This lesson is about soaring weather and thermals. So once you're past your initial phase of training, you're going to get a little bit tired of just gliding back to the airport from wherever the tow plane leaves you off. And it's time to start thinking about how you can keep your glider in the air for longer and sometimes even go some places. So in order to do that, you need to find some rising air. The most common way to find rising air, especially in Michigan, is thermals. There are some other ways that we'll talk about in later lessons. So this lesson covers the atmospheric phenomena that cause thermals to happen, and then we'll talk about some of the techniques that make the best use of those thermals when you can find them. So I'll start off talking about atmospheric stability and how thermals form. And then we'll talk about how you find them when you're out flying in the glider, how you center a thermal once you've found one, what bank, angle, and speed you should fly in order to maximize your performance and get the most out of the thermal. Then finally, we'll talk a little bit about how to avoid hitting other gliders when you're sharing a thermal with them. So in our gliders, we fly in the lowest layer of the atmosphere, which is called the troposphere. Each different layer of the atmosphere has sort of different properties. And the troposphere is the one that we care about. The temperature in the troposphere tends to gradually decrease with altitude. Now, how much it decreases as a function of altitude varies a lot from one day to the other and from one time of day to another. So this graph on the left is showing sort of a standard atmosphere model, and which is kind of an average temperature versus altitude. Um, and on average, the temperature decreases about 2 degrees Celsius per 1,000 feet in the troposphere. That is called the standard lapse rate, which will be different than some of the other lapse rates we'll talk about later. The pressure in throughout the atmosphere is determined by the weight of the air that's above that level of the atmosphere. Um, and up to about 10,000 feet, the pressure decreases about 1 inch of mercury per 1,000 feet. So as air moves around, it tends to move, if there's an area of high pressure and an area of low pressure, that tends to push the air from the high pressure area to the low pressure. And as the air moves to a lower pressure area, it expands. And as it expands, it cools down, even without any heat being added or subtracted from that parcel of air. It cools down just because of the fact that it's expanding. So in if there's a parcel of air that's moving vertically in the atmosphere, if it's going upward and condensation is not occurring, which means clouds are not forming, that air will expand because it's moving into an area of lower pressure. And as that expansion will cause it to cool at a rate of 3 degrees centigrade per 1,000 feet. You notice that's a little bit higher than what the standard lapse rate is. So that value is called the dry adiabatic lapse rate. The dry refers to the fact that condensation is not occurring, so we're not getting any cloud formation. So if there is moisture in the air and that moisture is condensing, then the air will cool at a slower rate than it would otherwise. The exact rate is not a constant. It varies a little bit with pressure and altitude. It's between 1.2 and 2.2 degrees centigrade per 1,000 feet. So this value is called the adiabatic, the saturated adiabatic lapse rate. So this chart shows two different situations that can occur in the atmosphere when the actual lapse rate is either higher or lower. So on the left here, we have a situation where in both situations, it's about 20 degrees Celsius at the surface. But in the situation on the left, the temperature is 9 degrees Celsius at 3,000 feet. And in the situation in the right, it's 13 degrees Celsius at 3,000 feet. So the actual lapse rate is high in the left example and it's low in the right example. So like in this left example where the actual lapse rate is higher than the adiabatic lapse rate, this little piece of air here, if something forces it up from the surface to 3,000 feet, it will expand because the pressure is going down. It's a little exaggerated, the size of the balloon there, but because it expands, it will cool down. So it will cool down from 20 degrees to 11 degrees centigrade. That happens in both cases. But if the air around it, once it gets up to 3,000 feet, is 9 degrees, then because it's warmer than the air around it, it will continue to go up higher. In the right-hand case, it will be cooler than the air around it, so it will tend to drop in that case. So if something starts going up but then comes back down, that's kind of a stable condition. It tends to, even if something starts it happening, it just undoes itself and goes back to how it was. That's a stable situation. The air tends not to move very much. Whereas in situation A, if you start air moving, it tends to keep moving even more. So that's an situation A is an unstable situation. Unstable is the situation to me that we like when we're looking for thermals. So high actual lapse rate corresponds to unstable atmosphere and good thermal conditions. So one way that we measure the degree of stability in the atmosphere is with something called the thermal index. The thermal index is a function of altitude, and the formula for calculating it is based on observing the temperature at the surface, the temperature at that altitude, the difference in height between the elevation of the surface and the altitude, and then the dry adiabatic lapse rate. So get all those numbers and you get an index. If the thermal index is a positive number, then there won't be any thermals that reach that altitude. If it's a negative number, depending on how negative it is, it may be like if it's just a little bit negative, then you get weak lift. If it's a quite a bit negative number, like less than -6, then you have really good thermals up to the altitude in question. So this picture shows a little bit about how thermals form and dissipate. They're not all the same. There's a lot of variety in thermals, but this is kind of a illustrative example of a typical one. So the over time, in this second view here, something is causing a warm spot near the surface here, and that starts the air going up. It could a wind moving against a surface like that could be just a thing that triggers it to move up a little bit. And if you get instability, then once something starts the air moving up, it will tend to keep moving up. Here we've got a thermal in the second picture that's formed a little bit more, and it's extending uh, up to a higher altitude. And these little bits that look like snow up here are showing that it's just reaching a point where there is condensation starting to happen. As the as that air is cooling, it eventually gets down to its dew point and the moisture starts to condense. In the next couple pictures, it's extending a little higher, and this cumulus cloud is getting a little bit bigger. At this point, it's kind of like maybe all the warm air that was near the surface here has kind of already gone up and the thermal has stopped being produced anymore. It will continue to be existing kind of at altitude, but won't you won't see much thermal happening down here. Once that happens, eventually it dissipates. The cloud may stay in place, but the but you're no longer getting this nice updraft of air under the cloud, and you can even get a lot of descending air. Um, so how do we find these if they're out there? Finding thermals is a it's a skill that takes a lot of time to develop. It's not something you will be any kind of an expert at when you first get your private pilot's license. You learn it by practicing, by trial and error, and by talking with people who are good at it. Um, Best way is to take two-place glider where the other person is somebody who's experienced with soaring and can kind of explain their thought process and have you give your ideas and critique your missed thoughts and things. That helps a lot. But it's a time-consuming process to learn to be good at finding thermals. So some of the hints that you'll find. Uh, the best one is a growing cumulus cloud. So when you see a batch of clouds in the sky, some of those clouds are good markers of what's currently happening underneath them in the atmosphere. There are other clouds out there that are just remnants of things that happened hours ago or even days ago. And it takes practice to learn the difference between a cloud that's marking a thermal and a cloud that's just a remnant of something that happened before. Um, one one hint is that the ones that are remnants tend to be a little less defined boundaries around their edges than the others, but it just take practice looking at them and feedback from people who are more expert. Uh, Birds are good at finding thermals, and oftentimes other gliders are good at finding thermals. So if you see them circling, they've probably found a thermal, and if you go where they are, you'll probably find it too. Looking at the ground, you can kind of pick out areas that are likely to initiate a thermal. Um, Dark, dry areas tend to heat up more from sunshine than areas that are light colored or that have a lot of moisture. And the areas that heat up the most are where thermals are likely to form. So pavement, you know, blacktop is a good example. Lakes are the opposite. A lake is unlikely to be a place where a thermal would form. Hills that where one side of the hill faces the sun and the other side of the hill is in the shade, that tends to create a warmer spot on the well illuminated side and create a thermal. Thermals come in different shapes and different characteristics. There's a lot of variability. The left picture here is what's called a plume thermal. It goes from the ground all the way up to a fairly high altitude, and the air is rising through that whole altitude span. And these will tend to go on and stay in existence for quite a while and kind of stay put in one spot over the ground, even when the wind is blowing. The thermal on the right is more of a bubble thermal, that it's, one parcel of air is kind of moving up, but there isn't more filling in behind it necessarily. So if you were to fly under that, if you see a bunch of gliders circling in that and you think they'd be great to go get under them, you might not find much. So once we've found a thermal, our goal is to circle in that thermal, and we want to circle on the center of the thermal so that we will spend as much time as possible in a strong updraft part of the thermal. The first step to doing that is to figure out where you are, or where the center of the thermal is compared to where you are. In this example that's illustrated in the picture, if the glider is circling in the solid blue circle here, they're kind of touching the center of the thermal, but spending quite a bit of time away from it also. They will notice the variometer will be changing as they fly around that circle. So don't forget that your variometer has lag to it. So even though your climb rate will be best like in the position where the glider is illustrated, the variometer may reach its peak, say 90 degrees later. So the first step is recognizing that where the thermal is, and it's good to pay attention to landmarks on the ground to keep track of where they are. So this pilot needs to recognize that the center of the thermal is toward the lake from their current location. Then next thing to do is to shift the center of your circle. The couple ways to do that. One is you just wait until you're in the part of your circle where you're pointed in the direction that you want to shift it towards. Level the wings, wait a few seconds, and then start circling again. In this example, they kind of overcorrected and went to the other side of the center. Another way to do it is to sort of gradually change your angle of bank so that when you're moving away from the strongest lift, you use a high angle of bank to do a sharper turn. And when you're heading toward the stronger lift, you use a shallower angle of bank so that you go straighter. That will gradually move your circle over. Doing it too often, it can be a mistake. You need to kind of stay in a circle long enough for the pattern of which side is strong and which side is weak to be clear. If you're constantly making an adjustment, then it's really hard to observe where where you're at because while you're adjusting, you mess up your observation a little bit. And this is a skill that it just you won't. This isn't one you have to be good at when you take your private pilot practical test. You'll get you'll have some you'll have some skill at it, but you'll have a lot of time to get better at it after you start flying uh, as a licensed pilot. Okay, so we have to decide what bank angle we're going to fly when we're circling in the thermal and what speed to fly. So some things to know of is when you increase your bank angle and you're in coordinated flight, which you should be when you're circling in a thermal, your wing loading increases compared to what it would be when you're in level flight or straight flight. The increase in wing loading causes the speed for minimum sink rate to increase, and it also causes that sink rate itself to increase. So in the example in the graph here, we've got a glider that at 0 degrees bank might have a minimum sink speed of 50 knots and a roughly 150 um, foot per minute descent rate at that condition. As the angle of bank increases, to keep the minimum sink speed, they've got to go faster, and they eventually start to have dramatically higher sink rates as this angle gets steep. So on the one hand, the steep angle of bank is a problem because your sink rate's increasing. On the other hand, it's a good thing because it keeps your radius of turn small, and the radius of turn keeps you closer to the center of the thermal, where the updraft is stronger. So these two things kind of work against each other, and the question is, where is the best compromise, the optimum angle? So this graph kind of combines the information in that previous one in a little bit different form. The line indicates um, the, the sink speed as a function of the turn radius, with the dots being different amounts of bank angle that achieve those. So there's a real the trade-off here. To evaluate the trade-off, we need to know a little bit about the thermal and how much the the updraft speed of that thermal is changing as you move away from the center. So this is I plotted here an example thermal that um, is considered to be kind of a relatively typical thermal to the extent that there is such a thing. This is a 4.2 knot thermal that has 1,000-foot radius. You won't encounter this exact thermal, but it is sufficiently representative to be useful for the example here. And basically, what we see is that if we go past about 55 to 60 degree angle, we're actually increasing our sink rate so much that we're not even climbing at all. And this blue line here graphs the difference between the two, between the updraft speed and the sink rate. And between about 30 degrees bank and about 40 degrees bank. That's where the that's what turns out to be optimal with this particular example. Um, a different glider properties, different thermal properties. It wouldn't necessarily turn out exactly this, but that is a reasonably typical result. So it's a good place to work if you're when you don't have any reason to know that something else would be better. So as we learned in other lessons, the stall speed also increases as you increase the bank angle in coordinated, constant pitch angle um, flight. And in fact, it increases even faster than the minimum sink speed increases. So in addition to having, a too steep of an angle giving you issues with higher sink rate, the other thing it does is it narrows the margin between your sink speed and your stall speed. If we're sticking in that 30 to 40 degree range and a speed that is roughly 10% higher than the straight and level or straight minimum sink speed, then you've still got a pretty decent margin generally above the stall speed. And speaking of stalling, we have seen this kind of a chart before when we talked about some of the performance stuff, but in that lesson we were focused more on what happens at high speeds and how we avoid bending the glider. In this time, what I want to focus on is kind of what's happening in the lower speed end of this chart. So this has indicated speed on the x-axis and load factor on the y-axis. When we're thermaling, we're kind of in this low part of the curve at a little bit more than 1 for a load factor. And our margin over the stall speed is smaller than it is in most other times of flight, which increases the chance of having an inadvertent stall. So there are basically 3 things that can trigger a stall when you're at an airspeed that's close to your stall speed. One is if you have a speed reduction by accident. The second is if you pull back on the stick and create some g-forces. And the third is a vertical gust. These diagonal lines on this chart show different strength vertical gusts, and if you were starting from a straight, just flying along at 1G, and you hit a gust, that creates wing loading that can move you into a stalled condition. So the speed reduction part, we have a target speed. Our actual speed tends to vary from that a little bit because we are humans who are imperfect at controlling our speed. And the time when we tend to be most imperfect is when our brains are busy on other things. So when we're thermaling and our brain is busy trying to reason through, where the center of the thermal is and what I should do to move myself over closer to that center, my mind's doing a lot of things. That's a time where sometimes your speed can fluctuate a little bit from where you meant it to be. So you could get into an inverted stall situation. Changing in your pitch. If you're changing your bank angle in order to move yourself over to get more centered, then you're going to be making changes in pitch and changes in load factor. That if you're real close to stall, that could put you over the edge. And then the last thing, a vertical gust. Thermals are all about vertical changes in the air velocity. That's their whole. That's the whole reason we're interested in them. They a a nice thermal usually doesn't have a really rapid change in vertical speed over a short distance. They're not always nice. They sometimes at the edges there can be a lot of little rotors, um, and it's particularly true with low altitude thermals that tend to be narrow with pretty high vertical speeds in the center. They are the most likely to have vertical gusts in them, um, larger magnitude vertical gusts. So if we're, if we're up at 2,000 feet thermaling and we get an accidental stall, not a good thing, but it's not a huge thing because we have training. We know how to recover from stalls. Do what we're trained to do, recover from the stall, then get yourself back in the thermal and start climbing again. Low altitude stalls are a different matter. So the thermaling at low altitude, your likelihood of an accidental stall goes up, as well as the severity of an accidental stall. If you're hanging out very much with people who've been flying gliders for a long time, you're going to encounter people bragging about some of their low altitude saves where they got down to a few hundred feet and were all set up to land out and then found a great thermal and rode it up to 3,000 feet. Um, that's one situation where listening to the experienced people may be a bad thing. The other place that you're likely to see stories about attempted low altitude saves is if you read accident reports. The that's one of the categories that happens with regularity. People attempting low altitude saves, having an accidental stall, and coming to a very unfortunate end. So we talked earlier about one way to find your thermal is to notice other gliders that are already in the thermal. That means we end up with multiple gliders in the same thermal. We want them to not be at the same spot at the same time. So first rule for avoiding collisions when you're sharing thermals is to observe the direction that other gliders are turning. You can thermal turning left, you can thermal turning right, but if you come to if you see other gliders in the thermal turning left, you better turn left. Um, if you come to a thermal and you notice some gliders turning left and other gliders turning right, you better go find another thermal. Uh, it's you want to be turning the same direction as all the other gliders in the thermal. If there's another glider that is sort of close to you in altitude, then you want to try to stay on the opposite side of the turn. Basically, if when they're going north, you want to be going south. Um, You accomplish that by making, varying your turn rate so that you stay at that point. Staying opposite from them gives both gliders a good view of each other, and you're never pointed at each other. Sometimes the correction that you would make to center the thermal is a different correction than what you would make to keep yourself opposite the other glider. In that situation, collision avoidance takes precedence. You got to do the collision avoidance thing. If that leaves you not quite centered in the thermal, then oh well. Um, there's nothing that ruins your climb rate quite so quickly as contact with somebody else. Stall spin avoidance is even more important than usual if you've got a group of gliders in a thermal together. Um, a spin would be scary enough if you're the only glider around. Getting into a spin when there's a handful of gliders going different directions directly underneath you, um, a particularly bad time to find yourself in a spin situation. So a little extra margin over stall and being careful to stay coordinated. So in summary, uh, we all need to learn to work with thermal lift because that's the most common that we have. Even as we go around to other places, we may be able to find places that have ridge lift some of the year. May go find wave lift, but in most places, thermals are one of the primary ways that we have it. It's a long process to get proficient, uh, but you do gradually get better over time. So when you find a thermal, 30 to 40 degrees of bank angle and about 110% of the minimum sink speed that shows up in the glider's data. Conveniently, that tends to be about the same value as the glider's maximum glide ratio speed. And lastly, don't attempt low altitude saves.